VLF system. So I'm currently in the process of testing the VLF system. It was a design based on the prototype. So one of the things that I wanted to do was promote it and promote interest in it, because the data and information collected with these VLF systems is very important, and very important for science when you're trying to answer questions about the ionosphere and the magnetosphere and space weather, because a lot of these emissions are very much have relation to space weather, which is one of the main things that HamSCI is looking to study. So I just wanted to share, just to give a quick overview of the system and what you would kind of expect if you were a chosen site. Does everyone see my screen?
Sure do.
Okay. So this is what you would install outside. This is the VLF active antenna. Whoops. What you're seeing are the that's the preamp board. This is the actual antenna element. It's a foam pipe insulation foam covered in copper tape. And the reason why it's done like this and it's not just a wire or something else is because the foam absorbs vibrations, and with this sort of antenna, so this is kind of different than your typical amateur radio type antennas. The front end is high impedance, so you could think of it as a microphone amplifier, really, which is kind of what it is. So it has a high impedance input. So so it's very sensitive to small changes in capacitance, and with antennas, those changes in capacitance manifest themselves as vibrations can cause those small changes in capacitance, which is what you hear. So the antenna is actually microphonic. It's a good microphone. If a bird were to land on top of the PVC pipe and start chirping, you could actually hear the bird chirping through your VLF receiver. So it acts as a fairly good microphone. But that's why that we have this pipe in the pipe foam insulation to dampen vibrations. And this is what you're going to install at your house, and some of you might want to build. So it's just a PVC pipe with the foam insulation, and copper tape is the antenna element, and this preamp, and it's mounted to an aluminum mast. The other part of it is that it has to have an earth-ground connection. That's the other terminal of the antenna. So it acts as a virtual or a mirrored dipole, really. So this is basically what you would have to install at your house. Just a PVC pipe and a mast with some mast clamps. And this should be installed as far away from what would be as far away from anything containing a power line. So that includes aerial lines, that includes underground lines, that also includes structures like houses and garages and shacks that have power lines running in them. So think of power lines as radiators that are radiating interference, and you want to install this as far as possible from that. You also want to install it in an open field. It cannot work underneath a tree because a tree absorbs the E field, and the E field is the this is an E field antenna. So this is what you would install at your house, and and the only feed line that you would need is a Cat5 or Cat6 cable. That's it. That's all you would need. So just one Cat5 or Cat6 cable going from the shack to where the antenna is sited. And this is what you would put in your backyard. So it's not really a big, large antenna or anything like that. So this is kind of what we are asking. And then in the house or in the shack, the feed line from the antenna is going to come into is going to connect to this. This is the VLF interface box. And all this is this provides power to the VLF preamp through one pair and picks off the signal from the other pair and routes it out to an audio jack. And that audio jack is the VLF signal. And I say audio jack, not SMA jack or anything else like that, because we're dealing with VLF. So an audio jack is adequate. And then that is going to connect to a USB interface. So you could think of the USB interface as the RX888 that you plug into your computer. It has a USB port and it has antenna ports. So this audio USB interface it's a Behringer UMC 202 HD. So it's a 2-channel sound card is what it is, and it contains a high quality audio codec, which has been tested with this sort of system. Works quite well. You could also use the 4-channel version if you wanted to do a orthogonal loop antenna as well, which some systems are going to have. They're going to have an E-field antenna and 2 orthogonal loops for triple axis reception. But for the time being, this is what it is. It's just a box. And you connect the Cat 5 or 6 cable to these terminals. Power goes in here. You have a power indicator light, and then the signal goes into the sound card. And then also what goes into the sound card is the GPS interface. So what this is a simple GPS. It's a U-Blox M8T GPS timing receiver on an interface board, and it connects to a GPS antenna. It outputs a pulse per second signal, which goes into the other channel of the sound card. Now you could think of this as the GPS DO for the RX888 system, but it's a little different. The GPS DO provides a frequency reference, goes directly into the clock input of the RX888, but here we're not doing that. We don't have to, because we have software that allows use of commodity hardware, and it does some software tricks to use commodity hardware without modification. So all you have to do is feed a pulse per second signal into the other channel of the sound card. Now, this is actually not necessary if you're just doing natural radio reception. For the deployed systems, I would like to have this, but for those who want to build a system, this is going to be the most expensive component, unfortunately, because it's a GPS timing receiver. This U-Blox module here costs $96. It is expensive, and you can use lower cost GPSs. However, this provides the best performance, which is why that I chose it. But the main thing you want to have is an adjustable pulse per second output. So you want to adjust the voltage output of that, and you want to adjust it so it doesn't overload the sound card input. Um, but uh, uh, but this is the other component that you will have, and these systems will be pre-adjusted. Um, the ones that are going to be pre-assembled, they're going to be pre-adjusted plug and play. So you just put everything, plug everything together, and then turn everything on, and then it'll start collecting data. And so what it's going to do, it's going to sample the VLF spectrum up to 96 kilohertz. It's going to find the 60 hertz fundamental and notch it along with all of the harmonics, and it will track the fundamental, and it will adjust the notch to follow the drift of the power line frequency. So if you have a relatively quiet site, quiet hum, you could actually have a very nice sounding receiver. And so the science, so the data that we're looking for, we're looking for science data. And one of the primary things that you want to have is you want to capture these natural radio emissions. So the software will automatically capture them. And there's going to be a portal here that I am working on. So this is a website. It's an example. It is a website hosted by a VLF enthusiast. So these VLF systems, these 4 VLF systems, including this one, this is mine, will stream VLF data over the internet. The Grape and the RX888, they upload data, but in this case, we're dealing with audio, so we could stream it, actually. We could stream it uncompressed, we could stream it compressed. And for natural radio emissions, compressed streaming is often good enough. So what we want to do is we want to capture these natural radio emissions. This is actually one of the primary functions, because these are the most interesting, and these natural radio emissions are what are influenced by space weather. So we use these to study space weather. So you're going to have an interface like this. Your receiver is going to stream, and then what you're going to do is these are a gallery of spectrograms. Now, what you're seeing right now is a noise because Nathaniel's site became noisier. But the interesting signals, like these here, these are whistlers, and this is what we want to capture. And we want to capture these whistlers because we want to know at what latitudes do we get whistlers. Do we get more at higher latitudes or less? We want to kind of map it out, because when we map it out, we could understand the geometry of the magnetosphere. So whistlers are great tools in understanding the magnetosphere, and they often occur more frequently after geomagnetic events, not necessarily during, but after, when the magnetosphere is recovering, and it's charged with this extra material from the sun, and it could form these ducts, which propagate spherics and create these whistlers. So this is so we want to collect, we want to catch whistlers as much as we can. That's why that I named it the whistler catcher. We want to catch them as much as we can, because this is a very important metric in understanding space weather. And then the other part of it there's actually multiple types of observations, but this is one of the big ones. This is one of the most important ones. The other part of it is lightning location, and and I know that lightning location systems isn't necessarily the purview of HamSCI historically, but these VLF systems have the ability, since they're calibrated with GPSs, that they can take these precision measurements and measure what's called the time of group arrival for the spheric, which is the radio emission from the lightning stroke. And when you can get time of group arrivals from multiple VLF receivers, you could use geometry and some math to calculate and estimate where those strokes actually occurred, what the source of those spherics was. So this is ILDN, and this is and HamSCI has partnered with ILDN, and because the plan is to use the network of VLF receivers to where they're deployed, and to add to a global lightning detection network. And one of the reasons why that we would need one is because this is the only one right now that's open data, open hardware, and open software. There is an open data one, that's Blitzertung. That's the one that everybody knows. And then there's the ones that you pay for, Visela, which is very expensive. That's used by the professionals. But we want to have this information at the hands of researchers, low cost, open source. We want high schools to install these systems. We want everybody involved as much as possible. And through the genius of Paul Nicholson, who was unfortunately silent key, he was the one that wrote all of the software, that devised all of the math to build up this lightning location network. And he also wrote the software for the automated event detector, whistlers, to automatically detect whistlers. There's so much that these VLF systems can do. They are extremely capable. It all depends on your creativity and technical knowledge. And the best part about this is that anybody can do it. So what you're seeing here, this is a map of India, and we have some thunderstorm activity here. The colors indicate the age. So we have some thunderstorm activity here and here and here. This is useful information because with this information, we can use this to figure out what was the source spheric of a whistler. That's like the holy grail of whistler observation. Where did it originate? Where did it come from? Right. So whistlers they come from spherics that propagate out in the magnetosphere. But which specific spheric was it? Right. So that's good science information. So we need a lightning location network to give us this information. So that's why that it's so important. And this lightning location network in India, ILDN, is the first domestic lightning location network in India, and it's the first of its kind to be open data, open hardware, and open software. And we want to be part of that. So that's why with these systems we can do this. That's pretty much what I wanted to say. So what's upcoming is I plan on getting an information site up and running. Gary, I'm going to work with you to get an information page for the VLF system. This way, more people could read about it and understand it. It'll be the similar to the information page on the RX 888 system. So that'll be the start point, and it'll give you everything you need to build, install, operate, and all that stuff. So once I get some systems out for beta test, then I'm going to start packing systems, and we're going to figure out where we're going to deploy them. And if anyone is interested in hosting one of these, and for those who have rural areas, which are perfect for this, that's really what we're looking for. So if you have that, and if you're willing to host, that would be wonderful, because that's kind of what we're looking for here. Because suburban sites and urban sites, there's too much power line information, or power line interference, which won't necessarily make this system useful, because the interesting signals are being drowned out by power line interference. So that's why we have to be in these remote and rural sites. So if you do have one of those, then if you're interested, please reach out and we will set you up. But again, right now, things are still in the testing phase. I'm working as quick as I can to get everything done. But I do have a day job, so I'm kind of limited with what I can do in a short amount of time. But I am working towards getting all of this done, and getting all of this available for those interested and who could host and contribute, just like many of you contribute with your grape systems and your RX 888 systems and your magnetometers. So this is just another instrument, but it's a very important instrument which will complement HamSCI's current and future investigations.
Jonathan, I have a question.
Yes.
Are almost all of these whistlers from lightning strikes, or are some of them space weather? What's the deal?
The whistlers themselves always originate from lightning strokes. The other emissions, called dawn chorus and periodic emissions or risers, those originate in the magnetosphere, and those are generated by the interaction of, I believe it's the interaction with the material impacting the plasma in the magnetosphere.
Thank
So
you.
it's adding energy to the system. Basically, it's adding energy to the system, and the excess energy is being dissipated as radio waves. And in this case, the radio waves that are within the audio range and can be heard.
Thank you.
Yeah.
Gotta go.
Okay. Does anyone else have any questions?
Yes, Jonathan. What is the length limit on the cat cables?
It can go probably 400 or 500 feet pretty comfortably. Actually, it could probably go more, because the VLF interface box that I was showing you, that the feed connects to, it's interchangeable between a 24 volt and a 48 volt, or a 48 volt power supply. So if your drop is enough where you're going to lose with 24 volts, you could use a 48 volt, and it could go definitely more than 500 feet.
We
Jonathan?
need to be aware that the Cat 4 and Cat 5 specifications say 100 meters or roughly 300 feet. However, if you're not using actual 802.3 transmissions, you could probably link several cables together.
Right. So when I say Cat 5 and Cat 6, this isn't this isn't Ethernet. This is just the audio signal and power. And it's just convenient to use a Cat 5 and Cat 6 cable. But yeah. This is not 802 Ethernet or anything like that. So that limitation is specifically for 802 Ethernet and all that stuff. But in this case, this is a completely different type of signal, DC and a VLF signal. So we could actually go much farther.
Right. My only comment was that most of those Cat 5 and Cat 6 cables come in 100 meter lengths. So you're going to have to splice to get longer ones. Right.
And that's also possible too. And you could also use 500 feet, 1,000 feet spools too, things like that. But you don't need you don't need RJ45 connectors, as the connectors are just screw terminals and you're just connecting the individual wires. So it's connector agnostic, basically.
Jonathan?
Yes.
Hi, my name is Glenn. Couple of questions. You certainly went out of your way with the active antenna and the foam and everything else in there. My concern is how critical that environment is. For example, I could do everything in a nice, quiet environment. However, I'm in an earthquake zone. Yeah, I'm in Charleston, South Carolina. We have earthquakes. So even something like that, I'm sure is going to have an effect. You said, you can hear a bird landing on the antenna. So having a critical environment like this, I totally understand it. I mean, I really do understand it. But what happens when I fire up a kilowatt on 80 meters? All right, my antenna is going to be 500 feet out. My other wires are going to be 1,000 feet out. So you see the if let's say I'm at a school and I want to have this as a school project, I'm really thinking about the local schools that we sponsor. It's like, how can I do this? Because the only place they could put it is on the roof. So the environment here, where these things live, have you thought about how to put this in less critical environment? I mean, you notch out 60 hertz, for the power lines and things like that. I'm just trying to figure out how you could use this in a noisier environment. And that was my question.
Well, so the short answer is that you can't. You can't put it on the roof. Again, this is not a typical antenna used for frequencies higher than VLF. This is something different and specific. And what you're trying to avoid is ground loops. And what you might not notice as a ham is that the noise that you're trying to avoid at VLF is very prevalent. If that noise was present on the ham bands, then the ham bands wouldn't even be usable. That's how prevalent that this noise is on the VLF bands, which is why that you need to install this at these remote sites. So this is not something that can be installed at suburban sites or urban sites or on top of roofs or things like that. And it's just a limitation with how the antenna works. And the type of interference that you see in VLF. So it's unfortunately there's not really a way to improve it or change it or anything like that. It's just a limitation with the physics.
Okay, thanks.
Mhm.
Great, thanks, Jonathan. I think that stirs up some interest. Any last minute questions? Otherwise, we'll shut off the recording and call it an evening.
Good speech, Jonathan. Good talk. Good talk.
Thank you.
No, it's encouraging and exciting to see some of that hard work come together and see the new packaging and the circuit boards and all that, because I know there was a lot of dead bug construction and other things in the first version that's sitting there in Springbrook, PA right now. So this is nice to see. The GPS injector and whatnot too is a fantastic feature.
Thank you, Gary. Yeah, well, actually, running at Springbrook right now is the first build of one of these systems. So it is actually all the boards that I was talking about.
Oh, nice. Okay, that's why you guys were out digging in the snow over the winter, huh?
Yep.
Okay, gotcha. Okay, if there's nothing else, thanks everyone. Thanks for joining us. Remember, next week, Mary Lou will be talking to us about cosmic rays, and that'll probably be our last presentation of the year, and perhaps even our last session until next fall while we take the summer off. So that's it. 73, everyone. Thanks for joining and for all who contributed and those who stood by. 73.
73.
Bye.
See you on the air, Dave.